Hello everyone, I am Dr. Fawzul Atiq, giving some series of lecture for the course Discrete Mathematics. So today we'll discuss about the how to solve linear congruence, a system of linear congruence using the Chinese remainder theorem, and again we'll discuss about Fermat little theorem and some applications. So the first thing is find an inverse of 3 modulo 11. Now this problem we have done in the previous lecture also, in lecture number 20 also we have done, because the GCD of 3 comma 11 is 1, so you can find a unique inverse of it, right? So how to find that? Because GCD of 3 comma 11 is 1, because if this is 1, so we can always get a inverse of 3 modulo 11. So how to do that? First we will make GCD of linear combinations of GCD of 3 comma 11 as a linear combinations of 3 and 11. So how to do that? We have already seen it is, we'll try to do it 3 into 3 plus 2. So then again we'll do one more step. So 3 is equal to 2 into 1 plus 1. So our GCD already came. So I'll start with 1. So from there I get 1 is equal to 3 minus 2 into 1. And then 2, I'll replace this. 3 minus 2 is 11 minus 3 into 3. And outside there was 1, so we don't need to care. So if I do it, it is 3 into 4 minus 11 into 1. Right? And then from there, I can get at 3 into 4 minus 11 into 1 is congruent to 1 modulo 11. Why? Because this value is 0. But there is a factor here, and here it is modulo 11. So I can certainly write from there, it is 3 into 4 is congruent to 1 modulo 11. And from there I can get the final answer is inverse of 3 modulo 11 is 4. Therefore, inverse of 3 modulo 11 is 4. Because 3 into 4, it is 12, minus 1 is modulo 11. So in this way, we can find the inverse of some integer under modulo. Now, why we did that one? Because we are going to use this method in many places, right? To solve the linear congruence. Now, as we discussed, the 4 is the answer. Now, look at this linear congruence, and we need to solve it. Like, what is the linear congruence? And one example is 3x is congruent to 4 modulo 11. Right? Here, what you have to solve? What is the value of x? So that you can get 3 into 4 is congruent to 4 modulo 11. So how to do that? So our first job is find the inverse of, because this 3 and 11, their GCD is 1, so you can always get a solution of it. Right? Now first job is find the inverse of 3 more. First find the inverse of 3 modulo 11. But how to do that? We have done it in the previous program. What we got? That the inverse is actually 4. We already done in the previous one, right? So therefore, we already have 4 into 3 is congruent to 1 modulo 11, right? And then what you have to do? You have to get that like this portion. So you match with this one. 3x congruent to 4 modulo 11 you have to get, right? So how to do that? How to get that? So what you have to do, you write down that 3x is congruent to 4 modulo 11. This one we have done, right, in the previous one. Now this is the given linear congruence. We have to solve for x. What we will do, you multiply with 4, right, so that you will get 3 into 12. So then 4 into 3 x congruent to 4 into 4 16 modulo 11. Why I can do that? Because we know that if A is congruent to B mod n, then AC congruent to BC mod n. So I just multiplied with 4, that we can do it. But 4 into 3 is congruent to 1 mod 11. So this part is 1. So therefore 1 into x is congruent to 16 mod 11. And actually I got a solution. Therefore x is congruent to 16 mod 11. Right? X is congruent, but 16 is more than 11. So I can certainly write it as X is congruent to that 16. You can just make it that it's 11 into 1 plus 5. So 16 is 5 modulo 11. We are done. Right? Because why I just made it? Because 16 mod 11, I can write it as 5 mod 11. It is the remainder. So X is congruent to 5 mod 11. So we got a solution of it. So now you see that this X is equal to 5, we put 3 into 5, 15 minus 4 is congruent to 11 mod. Like it is 15 congruent to 4 mod 11. So we got the solution of this linear recurrence list. So if you get this kind of thing, so your first job is find an inverse modulo 11. And then from the given equation, you just adjust, you multiply with that inverse both sides, and you solve for X. I hope this is clear. Okay. Now this one we have already done. Yes, check this one. There is another one. Can you do that the same way? What is your first job? Find the inverse of 7 modulo 13, right? Because GCD of that, why you can get that? Because GCD of, so how to do that? GCD of 7 comma 13 is equal to, just a second. Yeah, 7 comma 13 is equal to 1. So we can always get a inverse of 7 modulo 13. How to do that? 13 is equal to 7 into 1, right? Plus 6. And then 7 is equal to 6 into 1 plus 1. So I got this GCD 1. So from there I can get as 1 is equal to 7 minus 6 into 1. Then 7 minus 6 into 1 is 6. Then 13 minus 7. And then I can get 7 into 2 minus 13 into 1. And then from this I can see that 7 into 2 minus 13 into 1 is congruent to 1 modulo 13. Right? And therefore, I can get 7 into 2 is congruent to 1 modulo 13. Therefore, 2 is the inverse of it. Right? 2 is the inverse of it. Now, once I get this 2, what is my next job? Then this one I got. Now, what is my next job? It is, you just match with this. You have 7x congruent to 3 mod 13. 7x congruent to 3 mod 13. What we'll do now? So just multiply with 2. So 7 into 2 x congruent to 6 modulo 30. And therefore, but 7 into 2 is 1. So x is congruent to 6 modulo 13. Our job is done. What is the solution? Therefore, solution is x is congruent to 6 mod 30 is the answer. Easy? Now, till now we solved one. Just so till now we solved a one single linear congruence, right? Now our next result is called the Chinese Remainder Theorem, which gives the guarantee that when you have some system of linear congruence and when it has a solution, right? So that theoretically, if you see that, like you may feel it is a bit difficult, like because from the language, but when I will solve the example, I think it will be very clear. What this theorem says, let n1, n2, nk be pairwise relatively primes integer which are all greater than 1. And a1, a2, ak be some any arbitrary integers, right? a1, a2, ak be any arbitrary integers. Then the system of k congruence, x is congruent to a1 mod n1, comma x is congruent to a2 mod n2, like that x is congruent to ak mod nk has unique solution modulo n equal to n1 into ak. So basically this n equal to this has a unique solution modulo n, right? So that means there is a guarantee that you can have a solution of this linear system of linear congruence. This system, that means some linear congruence you have that has a solution. It gives, if it satisfies, that's the first condition, n1, n2, nk are pairwise relatively positive integers, relatively prime positive integers. Okay, this has then some note is there. It says that you define the some new integer capital N1 is equal to n by small n1. What is n? N is equal to product of all this. Then n1, n2, nk, this way you define, right? Then what is the, from this we have actually a is equal to this a1, n1, y1, a2, a2, y2 plus dot, 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 up to ak, nk, yk as a is a inverse of like this is the actual the solution. And what is a1? A1 is our this numbers. It's already there in our congruence, some arbitrary number. That number a1, n1 is already defined. What is not defined? Y1, y2, y3. But what is y1? Y1 is the inverse of n1 modulo small n1. Y1 is the inverse of capital N1 modulo small n1. Like that, all yi are defined. Then finally, this value x, this is the solution. This gives you x is congruent to a modulo n is the solution of the given k congruences. Right. So maybe the theory looks little different to you, little theoretical, like what I am saying. But let us do an example so that it will be very clear to you. So solve the system of the congruence, this one. X is congruent to A mod 3, X is congruent to 2 mod 4, and X is congruent to 3 modulo 5. How to solve? So this is, what is this? This is A1, right? According to our notation, and this is small n1. Then again, this is A2, this is small n2. This is A3, this is small n3. The notation of Chinese remainder theorem, you see, this is the notation now. X congruent to A1 mod N1, X congruent to A2 mod N2, X congruent to AK mod NK, like that. So I have A1 is 1, N1 is 3, A2 is 2, N2 is 4, like that we define. Now, what is our small n? N is the product of all. So here we have, maybe I can write it as let N1 is equal to 3, N2 is equal to what? 4, and N3 is equal to 5. Now look at that Chinese remainder theorem. Conditions are satisfying or not? They all are pairwise relatively prime. That means there, if you take two pair and their GCD is 1. So they are all pairwise relatively prime. Correct? So they are all pairwise relatively prime. So our Chinese remainder theorem, all conditions are satisfied. Then we have the small n, which is the product of all n. So n1, n2, and n3. So if you do the product, 3 into 4 and 5, so it is 60. Right? So according to Chinese remainder theorem, n is this one. Now you have to define this capital N1, a small n by n1, capital N2, small n by n2, like that. So now what we'll do? What is capital N1 then? N1 is equal to small n divided by small n1. So 60 divided by what is n1? It is 3. So capital N1 is 20. Similarly, capital N2 is what? 20. 60 divided by 4. It is 15. Similarly, capital N3 is what? It is 60 divided by 5. So it is 12. Right? So how are N1 we got? A1, A2, A3 also we have. What is not, what we do not have in the solution, that Y1, Y2, Y3 we do not have. What is Y1? Yi is the inverse of Ni modulo N1. Right? So what I have to do? I have to find the inverse of find the inverses. So basically I have to solve three solutions. So 2 y1 congruent to 1 modulo that first one, right? N. So this is n1, which is 3. So this one I have to solve. So I have to find the inverse of 20 modulo 3. But this problem we have done in the previous 2 lectures. But see here, this 20 is a bigger number than 3, na? So we can always simplify this. What we'll do? So I have this one, but I can certainly make that 20y1 minus, I can do something that, okay, which is divisible by 3, and so that I can subtract that. I can always have that. So it might be, I can write it as 18 into y1. It is divisible by 3 now. So this will not make any effect, which is again congruent to 1 mod 3. Right? And therefore I get it as 2y1 is congruent to 1 mod 3. Easily we have done. Now this one, can you tell me the sum y1 which satisfy this that recurrence, this modular equation? So what will be the value? By looking at it also we can do. y equal to 1 will not satisfy, but 2, yes, 2 into 2 is congruent to, so therefore y1 is equal to 2. This is one solution I got, right? Similarly, that I have to solve that another one, which is 15 y2 is congruent to 1 modulo n2. What is n2? N2 is 4. But again, this 15 is greater than 4, so I can certainly adjust something. So 15y2, and then what I'll do to make a small, to reduce this complexity, that that writing complexity, that I don't have to do much calculation. I just want to reduce it. So 15, and then something you should divide by 12 to make it some less. So what I'll do, I'll subtract with 12 by 2 because it is divisible by 4. So this is congruent to 1 modulo 4. And from there I can get as 3y2 is congruent to 1 modulo 4, right? But 3y2, what is the value of y2? So that you can get, so y2 equal to 1, no, 2, no, 3, 3 is a 9 minus 1, so it is satisfying. So y2 is equal to 3 is a solution, right? This way I can easily find the inverses. Then similarly I have to find the another inverse, y3. What is y3? Y3 is 12. Y3 is congruent to 1 mod n3 is 5. Now the same way if you do, the y3 value will be getting that 3, right? So I got a1, a2, a3. So a1, a2, a3, right? And then n1, n2, n3, all I got, and y1, y2, y3 also I got. So then I got the final solution. So according to the Chinese remainder theorem, A is equal to, this is the solution to the given k congruences under modulo n, small n. So A1, N1, Y1. Like this I have to do. Therefore, what is the value of A? A is equal to A1, N1, Y1 plus A2, N2, Y2 plus A3, N3, Y3. If you write them, then finally you can just simplify it. You will actually get 40 plus 90 plus 108, right? And this all together, it makes you a 238, right? Hence, what we got? Hence, x is congruent to 238 modulo 60 is the solution of it. But again, 238 is bigger than 60. I can certainly reduce this one. So x is congruent to that 6 divisible now 180. I can do it. 238 is equal to 180 plus 58. Correct? So this is 230 is equal to, maybe I can write it as 230 means it is 180 plus 58 modulus 60. And as I said that it is divisible, 180 is divisible by 60. So I can reduce that part. So I can say x is congruent to 58 modulo 60. Our job is done. You see that x is congruent to 58 modulo 60 is a solution for the given recurrence, the given system of linear components. Check. 58 you put it, 58 minus 1. It is 57. Mod 3. Yes, correct. Again, 58 you put it here, 58 minus 2. So 56 is congruent to, 58 is congruent to 2 mod 4. Yes, satisfying. 58 is congruent to 3 mod 5. Yes, 58 minus 3, it is 55, which is divisible by 5. So it is the solution of the general solution of this system of linear congruences. Right? So using the this Chinese remainder theorem, one can solve a system of linear congruences in this way. So practice such kind of a problem. 2, 3, once you do, then you will see that it is very easy. Right? So practice such kind of problem 2, 3 so that you will feel it easy. Yes, so the whole solution in that in type form, it is there. You can see the full solution is written. Now next is we'll discuss about the Fermat-Little theorem. What Fermat-Little theorem says that if p is a prime number and if p does not divide a, if p is a prime number and p does not divide a, where a is any integer, then a to the power p minus 1 is congruent to 1 modulo p. If p is prime and p does not divide a, then a is an, where a is an integer, then a to the power p minus 1 is congruent to 1 modulo p. Now, this Fermat-Little theorem are very, very useful to find the to find the remainder term in many cases, right? Look at this example. Find the remainder when 7 to the power 242 is divisible by 3, right? So you have to find. So basically, you have to find the solution of 7 to the power 242 is congruent to x modulo 13. You basically have to find the solution of this, right? So how to do that? So it is like we will apply the Fermat theorem. What Fermat theorem says that if p is a prime and p does not divide a, where a is an integer, then a to the power p minus 1 is congruent to 1 modulo p. So we have 13 is a prime number and which does not divide 7, right? So what we'll do, by Fermat theorem, we have, maybe I am writing it as by Fermat theorem, right? As 13 does not divide 7. So I have this will imply that 7 to the power 13 minus 1 is congruent to 1 mod 13. This one I can write. Now this is what? So 7 to the power 12 is congruent to 1 modulo 30. This I can say. But our look at the question. It is given as 7 to the power 242. Right? So I have to make that, to make this one, I have to make this equation like that. How to do that? But 242, I'll write it in terms of 12. Right? So 242 is equal to, I can have 20 into 12, so which is 240 plus 2. Right? So then I'll first multiply these things with 20, like I'll make a power of it. So then, because we know that if a is congruent to b mod n, then a to the power n, a to the power some integer, a to the power k congruent to b to the power k mod n, right? So that thing I am doing. So I am, from there I am doing it something that which implies that the above one implies 7 to the power 12 whole to the power 20 is congruent to 1 to the power 20 modulo 13. And therefore 7 to the power 240 is congruent to 1 modulo 13. So we are almost close to it. But still I have to get 242. So how to get it? So 7 to the power 240 I got. Now what I'll do, we know that A congruent to B mod n, then A into C congruent to B into C mod n. We all know, right? So that thing we'll do. So what we'll do, 7 to the power 240 into, I am multiplying 7 square both sides, which is equal to 7 square mod 13. Right? So then now I got this side answer. So 2 to the power 7 to the power 242 is congruent to 7 square means 49 mod 30. We got actually the solution of it. 7 to the power 242 is congruent to 49 mod 30. Right? And then if we got this one, but this is again a big number, then 13, I can still reduce it. 14 mod 13. That means what is the remainder if you divide these things by 30? So we can always make, reduce it, right? So how to do it? 49, then I can make it that you just make 49 is equal to 313 plus 10, right? So then this part I can remove it. So the 10 will be the answer. So therefore I got, therefore 7 to the power 242 is congruent to 10 modulo 13. I actually got the solution of it, solution of this equation, which gives you the remainder when you divide 7 to the power 242 by 30. So the final answer is 10. Correct? So this is the, formally I have done it here. You can check it this one also, or you can do it in this way. Right? We have the last one, which is the statement only will do, the Euler's theorem. What Euler's theorem said, that let, it is the generalization of Fermat theorem basically. Let a and n be integers with n greater than 0, then a to the power phi of n is congruent to 1 modulo n, where phi n is the number of positive integer less than n and prime to n. right? So this is another important result. You just remember the statement. Whenever you can apply apply this theorem. Some results are related, right? A to the power phi of n is congruent to 1 mod n. So here in the Fermat theorem, it was a prime number and a to the power p minus 1 was. So the note is, if you replace this n by p, then phi of p is actually p minus 1, right? So if you apply this n equal to p, and Euler's theorem gives you that a to the power p minus 1 is congruent to 1 modulo p. But this is the basically the formality theorem, isn't it? Right? So all the content I have taken from this book only, and you practice this such kind of a problem. I hope you enjoyed the video, and if you like it, please like the video. If this is helpful for you, write the feedback how you want, and I think this channel is helpful for you. You can subscribe this channel because there are many other set of lectures are also there, like probability and statistics. I'm sure that in future it will going to help you. Thank you very much. We'll meet in some another lecture. Bye bye.